I think we might as well start.
Okay, thanks for whoever stuck it out until today. So, so let me start by recalling where we ended up last time, and this time maybe take a bit more time to go over this because this might be useful for other applications. So if you remember, we ended up trying to prove an analog or some kind of a compromised version, so as to speak, of this differential inequality, which will enable us to prove that the truncated connection probabilities are actually comparable to the corresponding probabilities. Sorry, the connection probabilities for the truncated guys, for the truncated models, okay, who are finite range, are comparable up to a small additive error with the same probabilities for the full model. So this is the model defined with respect to the level set of the full Gaussian free field. And using that, then we will be able to arrive at a contradiction, which we outlined last time. And this, in an attempt to prove this differential or something like this, because we will not be able to prove this one, as we saw last time. So we first convert them to their corresponding, the expression in terms of probabilities, which involve the pivotality event. And recall the pivotality event is essentially the fact that the point X is crucial for the connection between these two sets. Okay, so what it means is that if there is a path, there's a one arm extending from X to one of the sets and another arm extending from this to the another set, to the other set that you are trying to connect, and they both pass, that is, they come all the way up to X. So if X is open, you have a connected path between the two sets, but at the same time, you also have a closed cut set or dual surface, as it's called popularly, which also passes through X, which means that if X is not open, okay, if X is not in your level set, then, well, you don't have a connection. Okay, so X is essential. Openness of X is essential to connecting these two sets. Now, so in terms of this event, what we have here is a conditional pivotality with respect to the threshold. Okay, so the difference is, of course, that in case, so this is true for level sets of arbitrary fields. So in particular, also Bernoulli percolation, which you also saw, in which case you have independent uniform fields instead of this. But there, this conditional probability doesn't bother you at all, because as you know, as we can see from the definition, the event pivotality is independent of the state of the vertex at X. Okay, so this just completely decorrelates these two events, and you just get the unconditional pivotality that you're used to seeing in the standard Rousseau's formula. Whereas in the time derivative, you just essentially what you have, you can obtain the same thing, just applying a chain rule. So you have a covariance term, which makes it all the more challenging. A covariance term with this xi x, which is kind of the difference, which is kind of the gradient. So if you remember, this is kind of the difference between the two successive layered fields, and this has range exactly ln, okay, at the current range that we are performing. So, and you slowly want to kind of increase this range, okay, to get closer to the original field as much as possible, okay, but not locally. Remember, that's because that's what we already have, but for events on arbitrarily large support. Okay, so again, we remember that for Bernoulli percolation, this would not be a problem. We'd just be able to, because xn is something, in that case would be, let's say, something, some field value at the point X itself, and as such is independent. of the event PX because everything is independent. So you'll be able to factorize these probabilities into terms of two probabilities. So from this, you'll get the probability of pivotality, and from this, you'll get this expected value of this, which is small because of this. And then this is just follows immediately. But you don't have that, of course, because the range IN is very big. Okay, and that was the problem. So because if you just do, So in order to do that, let me pass through that. What we came down to is that this is the main thing that we'd like to do, something like that. Let's just focus on the case where the fill value is atypically large, okay? Because other case we can take care of simply by monotonicity of expectation. That's not a problem at all, because that's exactly what you would like, this kind of term. So this is the real problematic term, which still involves the tail of this Gaussian variable of range Ln at x. And this is atypical, but unfortunately you cannot decouple that. You cannot factorize these properties. But we would still like something like that, okay? Okay. So the idea is that, well, that we talked about is that we nevertheless would like to decouple, okay, right? We would nevertheless like to somehow factorize this too, but since we cannot do it with p of x, well, what we do is that we replace this p of x by monotonicity, by just simple inclusion, with a bigger event, which we called coarse pivotality, such as nothing but substituting a bigger domain or a ball, okay, for the point x, okay? It's the same thing. So again, just replace the point in your mind with this ball. Again, we have the similar picture. You have two paths, two arms extending from this to the two sets. Okay, so if the ball is open, you end up connecting these two sets. And at the same time, you have the dual surface extending all the way to this ball. So if you close all the vertices in this ball, this dual surface disconnects these 2 points, these two sets. Okay, so what's the advantage of that? Advantage of this is that we forgot the dual surface as well as the paths inside this ball, okay? Now, since the range of dependence of xi xn is Ln, and this event is basically dependent on whatever happens outside this ball, right? Because nothing happens inside can affect this blue or red part. Well, now actually we can use this classical thing that, well, now replacing that by the bigger event, these two things become independent. So now we can do our desired factorization. So it comes out and it gets you a state exponential prefactor, which is very good. But the problem is that, well, what you get, of course, is not pivotality, but something coarse pivotality. Okay, so probability of this ball, which is bigger events, to be bigger than the pivotality. But of course, you cannot stop there. You have to convert this event to pivotality of points. Okay, you have to reduce this the radius of pivotality here. And remember again, the range Ln can be as big as possible. Okay, so you cannot do something very stupid. And as you see, whatever the stupid things you can do, we touched upon this last time. But on the positive side, what we have a very strong very small prefactor. Okay, so we can spare some, not much though, but we can spare, let's say, arbitrarily small exponential, or maybe anything like super polynomial. But let's say, as long as this can be compared to exponential of some log of Ln to the big power times probability of Py. This is good because that I can kill using this. Okay, so let's keep that in mind, but let's see how one can do that. So there are two parts, right, to creating a pivotality. One part is, of course, the increasing part, which is extending this blue path all the way up to some point. And the second part, which is a bit more difficult, usually, is to construct surface, because construct surfaces are more difficult, because this is a surface, remember, okay? It's a thing of kind of a codimension one, if you can think of it like that. You have to extend all the way up to the point where you want to get pivotality, okay? You have to recreate this picture. So let's see, you have to recreate this picture. Okay. Now, usually you cannot hope to do that, but here we recall that we have two advantages, okay? Went to an assumption that our parameter lies in this fictitious regime, okay? So let's recall what are they? Again, that one part is that H is bigger than H tilde, which, if you recall, it means that here you are your disconnection probabilities. So kind of disconnection probabilities are, so probability, I'm just saying roughly, to connect, probability of disconnect is bigger than or equal to some C over L2 or D, okay? And since H is also less than H star star, again, recall that we talked about this multiple times, our connection probabilities are also polynomially bounded below, okay? So this two we have. But the thing is, well, there's a lot of problem still. They're true unconditionally, right? But here, you cannot just connect, right? You have to connect to particular things. You have to extend, rather. Yeah, it's a more correct term, because of course you will not disconnect to arbitrary big sets. That would be horrible. But in order to extend, you have to actually somehow reveal some information about these guys, okay? But that's very bad, because unlike Bernoulli percolation, revealing these things can give you immense negative information, okay? That can be, because remember, the field has and the model has an infinite range of determinants, okay? So you have to be very careful about that. Okay, so let's look at these problems a bit more closely. Okay, so first thing first. So this part we talked about again, but let's talk about it again. So what we first do here is that we want to construct the dual surface. Okay, let's do that first. It's the more difficult part, I believe, but we'll see not. Sure, the more difficult part would be to construct it up. Okay, so what do you do there? We use the fact that you have a disconnection probability a priori, right? So the idea is that I have this dual surface coming coming all the way up to the box of radius BLX. What I would like to do, I would like to disconnect BLX from a bigger box, thus giving me a dual surface like this. So let me just draw the picture. So you can see it here, okay? This purple. So this purple, together with this previously existing red surface, would give me a dual surface, right? Would give me a dual surface between the 2 points, the 2 sets, okay? Why can we do that? So there are 2 things, is that, again, remember, we have moved, okay, so you see there's this M here, and M is, recall, this is the distance, how far, so if the smaller, so this is the radius, the distance from which you can disconnect under the assumption that you're below H tilde. So there's a function U, remember that we're between UL and big L, big L. It's kind of the inverse of that. So now your capital L is the U of M, okay? So M is the bigger box, and little l is the U of that. So that's the inverse function. Anyways, so this throws you up throws you up by distance of e to the power polylog ln. Okay, that's nice. So why you can do that? Now, okay, this is not correct up to the epsilon delta, but this is the idea. Well, knowing what happens inside ln doesn't affect you, beyond the distance of L. Okay, so you can forget that. And if you forget the path inside this ball, inside this big ball, you can remember that. That's okay. You can remember the paths. This distance capital L is to allow, because, okay, what do you want to do? So you see, you have to remember these paths. Okay, they're long. You do not want to reconstruct them because that would be horrible to pay for. But the thing is, you see, by FKG, you can imagine that you can require this negative event here, okay, by paying the probability cost, the unconditional probability cost for creating a disconnection, okay, which we have from our assumption, okay. Let's again recall, this is, so capital L would be capital M because that's the bigger box. Okay, that's good because both are decreasing events, right? You have a dual surface, means you have a closed set and requiring another closed set. They're just both monotonic decreasing events, so you can require them together by FKG by paying this cost, which is the cost of building one disconnection. That's good. But the thing is that you also have to remember these two blue paths, which are increasing, by the way. But that seemingly messes up the FKG because, well, you have a monotonic events of different direction. So that's why there is this gap, Bm plus L. So we remember it, we push it a bit further, L apart, so that they don't really affect you, whatever happens inside after, inside this wiggle room of length L. Okay, so that's this idea. Okay, so we're past that stage. So we have constructed a dual surface. But now the question, main question is, how do you construct pivotal points? Okay, what does it mean? Well, it means that you have to extend this blue path, let's say one of this blue path, all the way up to the neighborhood some point on the dual surface, right? And that will give you a pivotal point, because that's exactly the difference. So this is the dual surface, means, you can imagine the cluster automatically extends all the way up to here. Okay. But what is the problem with that? Okay, what could be the natural ways of doing that? And we talked about some last time. Let's go over that again. There is a naive option. The naive option is, well, let's use this fact. Why not? Let's use H is less than A star star. So you have a polynomial lower bound and connection. So you just simply do that. Okay, you just draw from here to here by paying a polynomial price in length, and that's good because so how much is this distance? So this distance is like so the cost of that. So the cost is like m n to the power minus t. But remember, what is mn? Mn, let's say, I don't care about the particular number here, but remember, ln is exponential of some power of log L. So that's okay, because remember, I can pay this amount of cost because I have a stage exponential sitting in front to help me. Okay, so that I can pay for. But there, the problem is, again, what I mentioned earlier, is that you just don't connect unconditionally, right? You have to connect to a point on the dual surface, okay? But, well, but then you have to reveal this. You have to know where they are, where the surface is, and that will give you a huge negative information. Because what does it mean, this dual surface, that you have the closed on all these points, okay? Which is a big connected region, and your field is extremely dependent. So this information, this negative information will make it very hard, potentially make it very hard for you to actually construct this path, okay? So that doesn't work. The next thing is that, okay, maybe we can try to take a more brutal approach. The brutal approach will be, well, I'll just, use some kind of finite energy, right? I'll just forcibly open insert by, or if insertion tolerance, probably we talked about that, Bernoulli, that where actually I'll just start along a random, like fixed path and just open one by one like this, by force, by hand. Okay, first of all, the distance is too big. Okay, you cannot pay an exponential cost in that. Okay, there you will say something. Okay, I'll be a bit more clever. Okay, I'll use a combination of brutal and this approach and this fact that h is less than h. How so? Here is the way. Okay, yes, it is indeed true that revealing this would give you a strong negative information. But my underlying field is not the Gaussian free field. It's close to that. It has a very big range of dependence, but that's only Ln. Okay. So if I cannot come all the way up to here, I can maybe come all the way up to this, this black, this region demarcated by this black line, which is essentially an L neighborhood, okay, of the dual surface. Okay. What is the reason for doing that? Well, because my range of dependence is L. We have already seen that, as long as two sets are L separated in my graph, the fields don't influence each other. So I am pretty much free here. Okay. So I can probably just use this lower bound to come to all the way, maybe that's wrong, come all the way to some point here, just paying a polynomial cost. Okay. Here still you have to condition, you have to do a bit clever, you have to do it a bit cleverly, because this region you have to condition, but you can imagine that's possible. Okay, that's morally true. Okay, fine. But what about the remaining L part? Okay, there you cannot do any more tricks. Then you can say, okay, now actually I'll do brutally. So what I'll do is I will start from here and go brutally point by point, opening along the way, okay, by paying a constant price, because that might be good. Well, that's still not good, because they were still L away, and you cannot quite pay this exponential in L cost, which, if you remember, we can afford up to a state exponential. But that's not the big problem, because that's state exponential for high dimension. You can actually, because the Gaussian free field becomes this fields, this Zions that I showed to you, they become thinner and thinner in high dimensions. In high dimensions, actually, you can afford an exponential cost. But that's not the main point. That's not the conceptual variable. The thing is that, as I probably mentioned to you in the very beginning of the lecture, the first lecture, that you do not have a finite energy or insertion tolerance of any kind. In fact, what you have is something very daunting, and let me tell it anyway. So this phenomena is called entropic repulsion for this kind of fields. This is also true for random interlacement. So if you condition, let's say you're surrounded by negative information. Okay, so let's say you have the following thing: your field phi x, okay, is less than 0, although you have not phi x but L. But anyways, we are now in a domain within the range of dependence of phi L, where actually phi L, as you saw, is very close to your original phi. Okay, so this behavior should be very much similar in this way, because this is the real playing ground. Okay, for all x in, let's say, Bn minus 0, okay, so I'm just conditioning on every other point. Let's say I'm surrounded by negative information, okay. What will happen in Bernoulli? It will not affect much. Right? We'll still have a probability of opening the origin with P. But if you look at here, in this case, phi 0, this will kind of follow as a, let's say, something like normal, but it would be centered around, let's say, so let's put it this way. This centers around C times square root of log n. Okay. Which will cost you to open this vertex, minus. Which will cost you like a polynomial in n number, okay, probability to open this up. This is a fact. This is known from the work of Zituni, Boltholz, and Deutschel, Lineantes, and more recent works. This is a characteristic feature of these kinds of models. Okay. Okay, so you don't have that hope. Okay, don't even imagine. So you cannot actually, unfortunately, use finite energy in any way. So what do? You nevertheless would like to connect. You have to create pivotal points like that. So what you do? Okay, you nevertheless perform this step. Okay, draw a bit closure. That might help. That is, anyways, not harm. So what is the situation we are right now? So we are at Ln distance from the dual surface, right? So that's actually what you saw here. So that means this ball of radius Ln around it is pivotal. Okay, I have the paths extending all the way up to that ball and the dual surface passing through that. So what I ended up creating by paying a polynomial in MM, a bunch of coarse pivotal points, but closed. That's important. So we no longer have to construct the dual surface of radius Ln. Okay, which we'll have to breach. Okay. Now, how to do that? How to breach this final thing? So I'll come to this description later. So, but let me just, you don't have to immediately parse all of this. But what is trying to tell you is something like the following. So what we'll construct is that, so what is the silver lining here is that this radius is big, okay, this region. Okay, and I know this boxes are far away from my balls. Okay, so this ball is of finite length. You can imagine these two boxes can stretch to infinity, nearby origin. Okay. As a consequence, what I have a huge exposed dual surface. What does that enable me to do? While I cannot, because of this fact that entropic repulsion that I talked to you about, while I cannot connect them brutally by a path because there's not a good region, what I can nevertheless do is the following, that I can try to find good tunnels in a sense, something like, and I'll show you the pictures soon. So like tunnels within which the effect of this negative information will somehow be mitigated. Okay, and that will allow me to draw this kind of paths that I would be able to do if I had no negative information present. Okay, and why you can find such tunnels? Because there are lots of places to find them. Okay, this is a very TLDR version of that, but that gives you some idea. So let me, I'll describe to you very precisely what that means, what this constant, I'll come back to you, but let me show you the picture first. So what's happening? Okay, so here you have two clusters, imagine, this S1 and S2 extending to you, and you have this distance which is like L, okay, to breach. So what I mean by this good tunnel or breach, or croissant actually, because you have this kind of fat middle portion tapering off towards the two ends. So this is kind of a sequence of these boxes where within each of this box you have a very particular condition. So what do I mean? So remember that, okay, so let me talk about that here. If you take this box of radius LK, and remember that I have this decomposition of phi, right? So I can decompose phi, let's say phi L, that doesn't matter. L is our current range of dependence, which is strictly bigger than LK, as phi LK, okay, plus this difference. I have not done nothing interesting till now, but remember there's this decomposition, right? So let's go back to this. I think so. Let's recall this decomposition. because they are all independent. Okay, we did this thing in the first day and also on the second day. So we can decompose phi, our fields, the sum of independent Gaussian fields with range of dependence being ln's for each n. Okay, so that's actually what I'm doing here. So let's get back. Okay, so these two parts are independent. Now, if you look at the field value here, so let's see. If you look at the field value in these two sets, so if I want to, I want to reveal these two sets, okay, that they are the two connected components. So I have to potentially reveal some negative information, because knowing a connected component means that the outer boundary is closed. Right? That's okay, but how far they can they actually affect this box? Let's say this LK box situated here. Let's say this one. Okay. Well, again, I can affect this 2D decomposition. Okay, for this field here, phi LK plus phi minus phi LK. This phi minus phi LK, okay, no matter wherever you're doing, is completely independent of phi LK at any point x, right? So, and these are the potentially problematic ones, because you see the range of this guys is basically kind of L, because the range of this guy is capital LK, because superscript indicates the domain of dependence, the radius of domain of dependence. So what that means is that this part of the information that we get from these two sets do not bother anything within this box, as long as you are just considering phi LK. However, the part which corresponds to the same radius, which is phi, so let's say here you have so let's say, sorry, phi LK restricted to S1 union S2, that is the only part that bothers you, what happens within a BLKs. But the good thing about this is that the radius of dependence of this guy is only LK. So if I can make sure that whenever I have an LK box in this tunnel, that manages to stay bigger than LK distance away from these two sets, and that's exactly what you see here. So the distance between B and S1 union S2 is strictly bigger than LK, as long as for every K box in your tunnel. Okay, that's one of the condition that you require for a tunnel. Okay, if we do that, then within this BLK, my phi LK is completely free. Okay, this is not affected at all by whatever is happening here or here. Okay, but then you can say, okay, that's fine, the phi LK is free, but why is that good? I mean, we have to construct this path in the full field. Well, remember, again, it's just that whenever we are talking about a region of dimension that is of size, which is something like LK, phi LK actually is almost similar to any field, in particular also phi, even the full field phi, okay, on boxes of radius LK. What this means is that, well, so locally within this box, my phi LK is a good proxy for my original field. Okay, so I can replace that with the version that is not affected by this negative information. Still, there is a problem. What is the problem? The problem is that okay, but then you see there are lots of these. I mean, that's just for one given box, right? But you have to find this thing for you have to essentially find a tunnel where this kind of property is holding for each one of them, and there's so many ways of that not happening. So whether this really happened, I mean, what guarantees that you have this approximation holds for all of these boxes, and you can find a tunnel where this holds for all of the boxes. So that's the definition of a good tunnel. Okay, so
So exactly what I just talked about is written in this condition. It's basically saying that whenever you are in a box of radius BLK, your local version, okay, this is kind of, forget about the T, it's basically the phi LK that I showed you. Phi K that I showed you. So phi T is the original version, original model. Your local version is a good approximation, okay, is a good approximation, epsilon good approximation of your original field, okay? And the idea is that if you're able to find such a tunnel where this properties hold, okay, then you can just perform, so exactly what I told you, perform your, you can apply your regular estimates, okay? Because I know actually how to connect in the full field, and by this notion of goodness, I know that, okay, this negative information are not affecting me too much within these boxes, because I can just construct this crossing using my local field, which being, by virtue of being close to my original field, also inherit this kind of connection properties. So I can draw these lines, these paths to create a pivotal point, okay, to bridge the gap, hence the name bridge. But, well, what tells you that you can find such a tunnel, and if so, with what probability, with what cost? So that's a big proposition. So this is this one, that there is a good bridge between any pair of, and essentially macroscopic sets, big connected sets inside BL and Y, with a stretch exponentially, with probability that is close to 1 by stretch exponentially small number. Okay? So that's a hard theorem to prove. And the idea involves renormalization. So I'll give you a very, probably I'll try to give you an example of renormalization, but not be able to give you a proof of this today because a lot of things. But the part consists of two things. One part is completely deterministic, where actually you prove some kind of local criteria, okay, which is easy to manipulate in probabilistically, okay, that certain kinds of events happen at a local scales. And then there's a long arduous combinatorial argument to start from there and to arrive at the existence of this breach. So these conditions are local. If you can see, you know, you're actually putting some conditions on the local boxes in successive scales. And then actually what renormalization techniques enable you to do is to show that, you know, that at every scale, you cannot have bad boxes too far apart from each other. Okay, and using that, you can actually come up to say that the good boxes have to actually accumulate to form a connected structure like this. This is very interesting, but unfortunately, I'll not be able to do justice to this, so I'll refrain from that. But if you want to keep some kind of picture in your mind, it should be the following: that you know, you have two big exposed surfaces, and you have potentially many chances, many ways that you can build such bridges around. So, you know, you have many phrase chances to do that in different scales. So that gives you enough entropy to beat any odds you might otherwise have. Okay, so that's kind of the big idea. But this kind of approach is applicable for a wide variety of situations, okay? Because this is pretty robust. You know, you can obtain that beyond ZD also. Okay, actually, this was first done in something similar to that. Rodriguez drew it and reverse in a paper where they dealt with the graphs of the from G equals Z. Okay, so after that, it's just a calculation. Okay, so this is the version that you see here is the quantitative version analog of this picture that you see here. So these are the costs that you multiply. You pay a polynomial cost to build crossings to each of the scales, and it ultimately gives you, you know, at most e to the power polynomial cost. And at the end, what you ended up doing is that you ended up reducing everything to a pivotality of a point to the right-hand side, which you wanted by paying a cost that you can definitely pay for. Okay, because you have a stretch exponential wiggle room in the beginning. Okay, so that's kind of the basic idea. Hopefully I could make that, okay, so too hasty. By the way, let me just tell you, but in all of this thing, I didn't tell you where does the additive error come from. And that comes from this fact. You remember, I told you, right? I just told you, the reason actually this kind of thing succeeds is that you have a large exposed surfaces. And why do you have that? Why you can allow this S1, S2 to be large? Well, that's because you see, I'm assuming these boxes are far apart. This BR and B capital R are far apart. So since you have a blue path entering from all the way up to that ball, okay, you have to have since they are not connected, you have to have a large exposed surface which is shielding one from the anode, okay, and exposing a connected set, okay. But this cannot be true if your L is too big, let's say, or if these distances are too small, right? Because you don't have that kind of room. So this ball might overlap this box or this one, causing some degeneracy. And it just takes care of that. That's why you see an error in terms of the smallest radius. Okay, so that's the reason that you see that. Okay, I'll go to something different now, and it will be a bit lighter because I'll do some basic calculation, which will show how these things work. But feel free to ask me any questions if you want for this end. Okay, so hopefully now you are convinced that, well, at some level, that this A star star and H tilde are same. But there is a leap of faith you took with me, is that, well, that beyond these two thresholds, you have what you need. So bigger than A star star, you had stretch exponential decay of 2-point functions, which gives you a polylogarithmic size on the finite clusters. But why that is true, and as I told you, this was proven by Rodriguez and Stidman in 2012. And this somehow beautifully encapsulates the idea of renormalization I was referring to. So that's why it's a good excuse for me to go through that proof. So hold on with me and see how this is done. Okay, in this case, and what are the difficulties? Okay, so let's see. How do you prove? Let's starting from this. How can you get at this? Okay, so look at this picture. So this is the idea which was introduced by Stidman in the paper 2012. It's called this idea of recursion through cascading events. Okay, so let's look at that. Okay, so what kind of event we're interested in? We're interested in, let's say, a crossing event. Okay, a crossing between two big sets. Okay, let's say Ln minus. So let's choose a sequence of scales, which is basically a geometrically going scales, where capital L0 and little L0 will see the roles of that, but little L0 is simply the common ratio by which you increase in every scale. Okay, now what do we have here? We're interested in this event where you have a crossing from the smaller box to the bigger box. Okay. Okay. Now notice the following. What we want to do is that we'll break it up. We'll produce using this big crossing to smaller crossings in one scale below. Okay, so this is what happened. So you can see I can pave. So you see I can pave the boundary of this Ln minus 1 box. Okay, using using a boxes of radius. Let's see. Just give me a moment. Right. So essentially, okay, so epsilon is Ln box. I think my scale's a bit garbled, but that's okay. That will not bother us too much. So let's say these scales are, okay, yeah. So let's say these scales are like Ln minus 2 of that length, okay? And this is the one scale below that. So this is like the copy of the full one in a smaller scale, okay? Whatever the appropriate is that. So when you do that, you can easily check, and this is the reason why I'm taking annulus crossing rather than 0.2 annulus, that if I pave it not pave it everywhere, but pave it along, this coarse-grained lattice. Okay, so this x1, x2 are, let's say, ln minus 2 apart, probably, instead of ln minus 1, but that doesn't matter. So this gamma will automatically induce two smaller annuloid crossings in this box, two boxes. Okay, so thus producing this inclusion. So what do you see here? So ENX is producing two crossings in smaller scale. Okay, so I'm denoting them by n minus 1 because that's indicates the length of the scale, and x1 and x2 the corresponding centers. Okay, but what is important is that they're far away, and we'll use that. You'll see why. Okay, that x1 minus s to the L infinity distance is at least L over 2. You can definitely do that. Okay? So starting from E and x, I'm getting at these two events. Okay, now let's see how do you do in the hypothetical independent case, Bernoulli case. Okay, and then actually you'll see where you get why we cannot do that for GHF, of course. Okay, so let's start. So let's call Qn the probability of this event, probability of ENX. So what do we have this inclusion? So, and we're now dealing with independent case in the independent case. Okay, so what does this tell us? This, again, recall this by a union bound, and this inclusion, what to tell us, something like the following, is that Qn is less than or equal to ln minus 1 ZD intersected with BLN squared. So this is basically the number of boxes. This is basically the union bound here. Okay, I'm just applying a union bound over all possible choices. So, so that's basically the number of possible choices of pairs times Qn minus 1 squared. Why? Well, because remember, we're independent, right? So these two events, since these two are further apart by ln over 2, they're independent. So, and by translation invariance, of course. So I can just drop x. So it's just that. Well, what this immediately gives you a simple recursion bound, which is, so that's the number of, because remember, again, remember the size. So the common ratio is little L0, and I'm doing this coarse-grained lattice. So the number, the cardinality, sorry, here is essentially 12(0) plus 1 to the power d. Since I'm doing a square, I have 2d, that's okay, times Qn minus 1 square. Okay, now iterate. You iterate to obtain, this is at most 12(0) plus 1 times d times Q0 to the power 2 to the power n. Okay, so that's trivial. Okay, but let's see where does this land us. So recall that ln is L0 little L0 to the power n, and hence your 2 to the power n that we are getting here is less than or equal to ln to the power some c, little c. Yeah, sorry, what I meant to say is, sorry, it's the opposite direction, of course. Yes, I need the better bound. Ln to the power little c for some little c, which is which depends on capital L0 and L0. Okay, sorry, bigger than 0. So therefore, Qn, which we just found out to be 2L0 plus 1 to the power d times Q0 to the power ln to the power little c, right? Because it's 2 to the power n, and 2 to the power n is bigger than ln to the power little c, as you saw here. So what we need to conclude then, so this already gives us a stage exponential kind of bound, provided that this is the inside thing is less than. So that actually we have to require. Right? So that will give us the required stage exponential bound. Okay. Now that's true, right? Because why that is true? If you think in terms of the what does Q0 tell? Q0 would be some kind of scale. Well, remember what is Q0? Okay, so let's see if I can go to this one. So by my assumption that H is less than H star star, I have this annuli crossing probabilities, let's say L0 to L0. Along some subsequence, they go to 0. Okay, so I can choose them by choosing my L0, my beginning scale small enough, big enough. I can choose this to be as small as possible. Okay, and hence we're done. Okay, now this is very simple. Okay, but this gives you an idea of the overview of the argument that you might do for the Bernoulli percolation. Now let's see, but let's see what you can do for here. Okay, here you cannot definitely do. So in this case, when we have a Gaussian free field, let's see where this leads us to, and we'll have to introduce a very important idea called decoupling by splinking. So let's see. Okay. So what is the ideal picture for us? Let's so at this point we have to introduce some parameters. Okay. So because we have to tinker with that. So let's say instead of just E and X, I also introduce the parameter H, okay, which is the underlying parameter, because before that we didn't need to do that. So here is the ideal picture. Just following what we had before. Sorry. So if we can show that probability of ENX1 H intersected with ENX2 H. Now let me just quickly point out to you, this is actually bigger than or equal to Qn minus 1 H. This is the wrong direction though. We don't need that because we need the upper bound. But this is true because of the FKG, right? Because both are monotonic given. So the probability of intersection is bigger than or equal to productive probabilities. Okay, so in view of that, what we need, ideal thing is that what we did for Bernoulli is we'd like that to be square. Let's see if that is, we can do that. Now here, however, let us recall that the covariance between the field values, okay, now we're working with full field values, phi y as x minus 1, the distance between the 2 points to infinity, they're like they're the Green's function, right? So they vary like a small polynomial in the distance. This is not good. So you can imagine that, well, yeah, they are not independent, but they're almost, probably the correlation is not too big, but that's not good here. That's what we saw. Because we want to prove a stage exponential upper bound, that's what we want to prove, right? And we're incurring a polynomial error in the first step. So that doesn't just work. So here is a solution. And this is useful in so many different other contexts. Solution is allow. So you don't need to be too rigid about H. From starting from H, getting back at h. Okay, well, you can actually replace it with slightly smaller h, so that's to increase q minus 1. But that's okay, because as long as the wiggle room by which you shift is small enough. Okay, so let me write that down. Allow h to vary over successive scales as we iterate, okay, albeit very slightly so, so that we don't move too far from. The idea is that you can reduce the wiggle room as much as possible. Okay, how to do that? The idea is what I just told you while actually discussing this notion of good tunnel. Okay, so here's the thing. So let's draw two boxes. Okay, let's see, two boxes. Let's say this one is back, and here we draw another box which is far apart. Again, by the way, this idea is potentially can be used in general graphs. Let's say this is your x1 and this is your x2. Okay, and they are far away. And we would like to see how much does the event, occurrence of event here can affect the event here. Okay, particularly. Right. So there are the one way to do that, and kind of the only way probably in this case, is the following, and which we talked about, to decompose phi within each box as a sum of two components. One part is the local component. Okay, so the local that I talked to you about, local component, which is the advantage of which is that it's shielded from, it's kind of independent of anything that is happening outside. Component, and there is another part which is the kind of the harmony, kind of, if you think about like Mark, okay, I'll talk about that. But this part carries the long range dependence. Is responsible for the long range dependence. Okay, and this is the part we have to control to get a handle of the effect of this one or the other one. Okay. Now, what you can do is that you can say that the xi satisfies just like we did with the decomposition. It's an analog of that. That the supremum, the maximum variance. Okay. So it's with respect to let's say a twice bigger box. So, okay, so we'll say it. But anyways, we can choose it in a way so that this is at most ln to the power minus d minus 2. We can recognize this term again. And there are several ways to do that. One thing is by decomposition that I talked about. Another thing is just by looking at the, just by using the Markov property of Gaussian threefold, decomposing into a part which is the local Gaussian threefold and the harmonic part. Now, what is the advantage of this? Well, the advantage of this is that then the following happens is that you can require, right, with a stretch exponentially high probability that the maximum value of the field, sorry, I didn't completely finish the sentence, variance of z x, zy. Okay, so as a consequence of this, what you can require, so this will give a stretch exponential upper bound on the probability that, let's say, the maximum value of xi y over this box centered at x2 is bigger than let's say bigger than epsilon. That would be bad for me. Okay, now you can, this is just a simple union bulk, but what is the advantage of that? Advantage of this is that now we can write, hence we can write this intersection event that we are interested in first by simple monotonicity, just by simple monotonicity, the event at x1 at h intersected with epsilon n minus 1 x2 with h minus epsilon over 2. Okay, I'm just doing this plain thing that we did before, but here actually I introduced by monotonicity a slightly smaller parameter, and that increases the event, right? Why I did do that? Well, now I'll use the following. I'll use the local version of this event. Okay, so now I'll use the local version of this event psi. Okay, and at the same time, I will require the following, that the event that I just told you, that the maximum value of this the xi fill that carries your dependence xi x is bigger than epsilon over 2. Okay, all these things together, what this gives you. So let's see it in words. Okay, so what's the point of that? Because now actually we know just what we saw. So these two things, they are independent. So you can apply your previous thing. Okay, so what this will give you is that if this thing happens, if your if these two events happen, then it has to happen that either in psi you have a crossing event at this level, okay, because you already have a, remember, you have a, sorry, there's no 2 here. I don't know why that was there. It's just h. Okay, so you have a crossing at x2 at level h, okay, and you have decomposing it into 2 parts, psi and xi. Okay, so there are 2 things can happen. Either the crossing also exists at level h minus epsilon n over 2, okay, epsilon in some small number, we'll choose. If not, since phi equals to psi plus xi, okay, then it has to happen that the xi is actually atypically large, right? Because if psi is smaller than that, you have to actually manage the gap, because ultimately you have this crossing at a level h above h in the sum. Okay, so that means this xi is atypically large at some point. So this gives you this atypical event. So this inclusion, what it lends you at is essentially, and assuming that, because in this locally, as I told you always, in this case, that whenever you are looking at a box of radius ln minus 1, you're looking, the local field and the global field are comparable very well. So this probabilities is also very close to what you'll have for n minus 1 for the full field. So what do you have? Essentially, q n minus 1 h times, you have to pay for the fact that you are approximating the full field with a local field, but that's not much. Sorry, h minus epsilon n plus the error due to this thing, some epsilon n square ln to the power t minus 2. This is coming, sorry, I'm sorry, I just missed it. So this is coming from the fact that your variance is ln to the power minus d minus 2. Okay, this is a very neat, so let's see that. So we copy. So this is a very neat kind of recursion inequality, which is as close as you can hope to get for a dependent model. Okay. Why so? Now, actually, what you do, well, what you get here is collecting everything, is putting together the previous equation, something you put in the entropy term inside, and what you have is by monotonicity, you just replace this one by h minus epsilon. We can always do that, plus some kind of this additive error. C epsilon square ln to the power t minus 2. Okay. Now you can iterate this part. Okay. Choose epsilon n. So what do we need from epsilon n? So remember, this is the thing that will that you will accumulate. That is that dictates how far you go from the h in successive scales. Okay, so you choose that to be like something summable but small enough. Okay, that's actually what you want. So this then leads us to iterate to obtain Q and H. We can check that, but anyways, it's not hard to believe. I'm doing Q0 of H. Now you have come all the way down to scale 0. So you have accumulated all epsilon k's. So let's say k equals to 1 to n plus some additive error. Okay, so this is, you can do, this is just simply a bound for this, way to bound that, but there actually what comes is that you have to choose your commons, the common ratio beacon. Anyways, these things come out very naturally when you do this thing, but the main point here is you start with a parameter value. You cannot do what you want to do in Bernoulli percolation. You compromise a bit in terms of your underlying parameter. Okay, that's the main core version of this normalization. You start with the parameters version and you tweak the parameters in successive scales. Okay, to obtain something similar quantity at a different parameter value. And then when you come down at the lowest scale, this is called the triggering state. Okay, so we have come down here, but we need this to be small. So what we need, finally, one should be able to choose L0 large enough, and we soon see how, which probably depending on how it says that, this term that you're seeing here, 2L0 plus 1 times D times Q0 of H minus C epsilon, because this is the kind of the term that you get by summing epsilon over n square. So that's the distance, that's the total splinking that you make, is less than 1 over 4, say. Okay, say less than something, less than 1. Okay. But how can you do that? Right? What allows you to do that? Well, that's basically the condition. That's actually, but this is possible. This is possible as soon as your H minus C epsilon is strictly bigger than A star star. Because remember, what is Q0? Again, normalization. So it is this probability, right? That you cross the annulus, essentially. So that's the scale and you cross the annulus, okay, of twice bigger radius. And that's precisely what you do, what you're asking for at scale 0. You're just asking for that, okay, given L0, I just want to make it as small as possible. Okay, I have this freedom. Hence, there's this thing that there's this L0, the beginning scale was important. This is called the triggering scale. So you have to trigger the normalization, and that's sometimes a very difficult problem. So what does your definition of A star star allows you is to trigger this normalization, okay? That, that it tells you that, okay, as long as you're strictly bigger than A star star, you know that your analyte crossing probabilities can be made arbitrarily small by choosing L0 big enough, okay? Because that's what the definition of L0. Well, but there is an epsilon here, but you don't care, right? Because epsilon is arbitrary. So it means that as long as you are strictly bigger than H star star, you arrive at a straight exponential decay. And there's a very generic approach to prove this kind of thing. In fact, the existence of bridge that I hinted at shortly before, it also involves a step like this. And the second thing is that, okay, I told you, fine, that A star star allows you to trigger the step, right? Sorry. But so A star star again, remember. But what proves that this is finite, right? And the thing is, you can actually run an argument in the same flavor as I pointed out, but for different types of events, which will give you that there is indeed a finite value of H above which you will have this property that that this analyte crossing probabilities will converge to 0 along some subsequence. Okay, but anyways, I thought that this generic argument would be good to keep in mind. So now let me use the last 15 minutes to just briefly give you the idea of what to do for the other part. So there's another part that is remaining is, this is the part that tell you that A star star. So above A star star, you have a stage exponential decay. That actually we did. But then there is another part. So what about H tilde equals H bar? And remember, H bar is this strongly percolative regime where you have big clusters locally and you connect them in a twice bigger box with high probability. Okay, and remember that we define H tilde, which is a mock version of that, again, which is essentially the regime where you have a disconnection, so the connection probability, which is, so connection, sorry, let me just draw a picture, I think that's better. Sorry. Bigger than or equal to 1 minus some epsilon L over L to the power T as L tends to, where epsilon L goes to 0. Okay, so you can make it as better as possible as L goes to infinity. So how do you do that? So how do you actually prove that? Well, if you have this kind of probabilities, good enough connection probabilities, from there, how can you attain uniqueness and existence of large clusters? And just give you this brief picture proof, not proof, but the basic sketch. What you first do here again, you run a renormalization process. And to do that, you first introduce another intermediate event, which is a bit weaker, okay, which you see here. So it's the same kind of thing, okay. Essentially, what you have here, you have a big crossing at some level, and you have uniqueness that you can connect any two such crossings in a twice bigger box. But the difference is that I allow some splintering here, okay, and that's important because of the reason that I just tried to explain to you, that while you run the normalization, if you're really a stickler for keeping the h same, the parameter values same throughout all the steps, you just get no hair because you cannot run these procedures. So you have to allow a more renormalization version of these events, and which is made possible by allowing some kind of wiggle loops. That's exactly what you're seeing here. You have a cluster for alpha, bigger than or equal to alpha at some level, but the uniqueness, they're connected. When you want to connect them, you say, okay, I allow you to go a bit below. Remember, when you go a bit below, you open up new connections, right? Because as you go below, as you lower the threshold, your level sets, your sets become bigger. So that's a weaker version of the event, that of the local uniqueness event that we have here. And well, I think I talked about it last time, but let's go over that once again. Why actually one is interested in defining this kind of events, you know, this uniqueness, existence? Well, the reason is that they are gluable. And what do I mean by that? So notice very carefully that you usually require a crossing to a longer region, okay? Whereas you require the uniqueness to a shorter, narrower region. And that's very typical. And that's useful because of the following case. So you see this picture. Let's say if you have two adjacent boxes for which this event happens, okay? Okay, so the one box is just a shifted version of the one on the left, okay, by half the side, by radius. And so these events happen for both of these boxes, okay? So for this one, then I have on path going all the way to the boundary of the box of radius 6 and on the same center. And so do I have for this one, okay? Right. So I do have for this guy. But for this guy, well, since this is a bit shifted, this can go in the wrong direction. So the picture is not completely correct, but probably it might stop a bit here. But no matter what it does, it has to cross by this condition, this annulus, okay? And that's the advantage, that you require uniqueness in a narrower region. So as soon as you have that, what you can do, well, now I have the clusters of these two adjacent boxes, both actually inducing a crossing to this annulus. And by this condition, I can join them. I can glue them in a slightly lower level, okay? And so if I have a, you know, array or like some kind of connected structure with these boxes instead of points, just like a coarse-grained kind of coarse-grained connected setup, then what I get is basically all these clusters through the adjacent boxes, they glue to each other by these properties, and they give you a very big cluster, okay? So that's this idea. And as I told you, the why actually you can hope this happen? Why is it true that you can this kind of event have good probability? So here's a statement for that, but let me just tell you why this is true. Well, as I told you last time, there's this picture of almost everywhere percolating subgraph. So we have this box, and what you can do is that you can draw small boxes everywhere inside, and in view of this strong lower bound here, okay, which has been designed to beat the union bound, okay? So even after doing the union bound, the failure probability is at most epsilon L, right? Because L to the power d is the volume. So what you have here is connections to the boundary everywhere, and this allows you to apply this argument by Benjamini and Tassio, which I no longer have the time to explain. But essentially, what his idea is that, okay, by allowing a bit of splinking. So in this case, that would be decreasing the level, allowing a bit more points to come in your set. Okay, so that, decrease the height a little bit, tiny bit. You'd be able to, let's say, you'd be able to connect all these things, points together, maybe in a twice bigger box. Okay. So, and the basic idea, if you just want to, as a take-home message, is that, again, the idea is about the idea of you have a long exposed surfaces. So, since you have these paths coming all the way in from the boundary, there are long interfaces, okay, that we can breach, that you can actually, by doing a splinking, as you come inside, you can connect them all together. But there are a lot of obstacles. It's not as easy as that. Even for Bernoulli percolation, it was a subject matter of paper, full paper, a very good paper. And for our case also, there's much more difficulty because of the fact that you have to deal with the strong dependence. Anyways, you can do that. And once you do that, so you come to this lemma. So you call the box L0 good now, where this event that you saw, it happens with a very good probability. Okay. So now what you want to do, you want to run a renormalization argument on a process of L0 boxes. Okay. And what do I mean by that? So let me just say in words. So now what you have here, instead of running boxes, instead of running a percolation process on points, you run that, with L0 boxes instead. Okay. So it's kind of the graph consisting of the L0 boxes. Okay. And what is the percolation process? So this belongs to your, let's say, part in your open. So this is, let's say, let me erase that. So where you say that open if and only if L0 good. Okay. And then what this new process on the coarse grain graph, okay, would basically look like a very strongly percolative regime of percolation. But it's not Bernoulli percolation. It's still dependent. So that's why you have to run this kind of renormalization argument that I just hinted at earlier. But the picture to keep in your mind is that the process of L0 good boxes, by virtue of this result, is now looks like a Bernoulli percolation, very strongly percolating Bernoulli percolation on this coarse grain graph. So that will give you essentially kind of a unique big cluster, okay, formed by these boxes. But then you have this nice property, because in all of these boxes, you have these properties, right? So by just this argument that I just told you, you can actually glue together these big clusters into one big giant cluster, and hence you'll get and anything which will basically subsume all the small clusters that you can find out, like, which is again a property that you can prove by normalization for strongly supercritical percolation processes. Anyway, so that gives rise to a result like that, which is basically, if you remember, the definition is basically close to the definition of local uniqueness. Okay, so this gives you that starting from any height below your H tilde with this good bounds for connection probabilities, and then applying this kind of renormalization argument, and of course this Benjamini Tassio argument, you can arrive at a picture where you have both of these with a stretch exponentially, with probability that is close to 1 by stretch exponentially small number. Okay. So this takes care of the renormalization parts of the argument. But again, what this leads us in is a very imprecise knowledge about what do the 2-point functions look like, right? So I'll end with that. So they look like some kind of stretch exponential, okay? But can you say something more? Can we probably, pin down the dependence on H or the exponent rho? Maybe is it possible? It doesn't seem to be possible. The kind of renormalization arguments I presented to you. Okay, there are 2 cores to pin that down, and in fact, they're actually quite difficult even for Bernoulli percolation. In non-planar dimension. But fortunately, in this case, these models actually enjoy a very nice and rich interplay with the potential theory of random walks. And by relating this connection probability to some properties of random walks, we can actually pin down this exponent and this precise dependence on H, which is related to the so-called near critical exponents, for those who know, in dimension 3, okay, which is very intuitive. And this is the thing that would be the subject matter of my last lecture, which would be lighter in content probably, but we have some more fun things from other areas of probability theory. Okay, so yeah, I think I'll stop here.